the last of the tests for convergence or divergence of an infinite series is going to be the root test. And similar to the ratio test, what we're going to do is we're going to take the limit as n approaches infinity, but unlike the ratio test, we're going to take the nth root of that series and the absolute value of it if it equals some value L. And what if L is a real number? If L is less than 1, then the infinite series is going to converge. If L is greater than 1, the infinite series is going to diverge. And then if L equals 1, we're going to choose another test because the root test is inconclusive. So the good news is the rules are the same for the root test as the ratio test. In fact, a lot of the same techniques for limits are going to be used as well. So let's take a look at some examples of employing the root test. And one of the dead giveaways that you're going to use the root test is if for some reason you have the nth power affixed to some sort of sequence that's inside of that comprises a series. So we have the nth power of 7 plus 5n squared, and then 6n squared minus 5, a series from n equals 1 to infinity. So we are going to take the limit as n approaches infinity of the nth root of the absolute value of 7n plus 5n squared divided by 6n squared minus 5. And all of that is to the nth power. Now, we know that an nth root and an nth power cancel each other out. And that's one of the benefits of using the root test here. There's no alternating sort of symbols going on here. So there's no minus 1 to the n or like a minus 1 to the n plus 1 or something like that. So what we're going to do is we're going to go ahead and just get rid of the absolute values. And we're going to have the limit as n approaches infinity of 7n plus 5n squared divided by 6n squared minus 5. And at this point, we just use our regular old sorts of ways to evaluate what our limit's going to be. And so we're just going to go ahead, divide everything by the highest power of n in the denominator, which is going to be n squared. And so we're going to get lim as n approaches infinity of 7n over n squared plus 5n squared over n squared divided by 6n squared divided by n squared minus 5 over n squared. If we simplify, we are going to get the limit as n approaches infinity of 7 over n plus 5 divided by 6 minus 5 over n squared. And now we can go ahead, we can employ the limit. These are going to go to 0, and we're left with 5/6. Now 5/6 is our limit L, or value L, and clearly L is less than 1. If we go back up, that means that we're going to have a convergent series. Okay, so we're going to say by the root test, we're going to say that the series n equals 1 to infinity of 7n plus 5n squared divided by 6n squared minus 5 to the nth power converges. Okay. All right. Another example, we have minus 1 to the n arctan of n to the nth power. And once again, what we're going to do is we're just going to use the root test because both of these are being raised to the nth power. So we can rewrite this as the limit as n approaches infinity of the nth root of the absolute value of minus 1 to the n divided by arctan of n to the nth power as well. The nth root is going to cancel out all the nth powers. And so at this point, we can go ahead and rewrite this as the limit as n approaches infinity of absolute value minus 1 over arctan n. And at this point, guys, we can go ahead and get rid of the minus 1 and take the absolute value of that to make it into a positive 1. So we're going to end up with the limit as n approaches infinity of 1 over arctan n. And then we have to remember what happens to the limit of the arctangent as it approaches infinity. And we might have seen this a few times, all right? But the graph of the arctangent function looks like this, right? Or approximately like that. And we know that it's going to have horizontal asymptotes as x approaches infinity, or I'm sorry, not pi, but x approaches infinity. Our y value is going to approach pi over 2. All right, so in reality, this becomes now 1 over pi over 2, which is 2 over pi. And we know that pi is about 3.14. And so we have 2 divided by 3 approximately, and 2/3 is 0.667. All right, but whatever it is, we could approximate it, and we know that the limit is going to be less than 1. All right. And once again, we look up at our root test, and it says that if L is less than 1, the series is going to converge. Okay, so by our root test, the original series, n equals 1 to infinity, minus 1 to the n, arctan of n to the n converges. Note that you could have used the alternating series test on this as well, all right, because it does alternate based on the power of n. However, the root test is a little bit easier to employ. Right? One last example is going to be this guy right here, the n times the third root of 4 to the n divided by 7 to the n. All right, so we are going to take the limit one more time as n approaches infinity. We're going to have the nth root of the absolute value of n third root of 4 to the n divided by 7 to the n. The absolute value has no bearing on these terms. And again, that's because we're going from 1 to infinity. All of these terms are going to be positive no matter what. So if we just kind of think about the domain of the integers 1, 2, 3, 4, 5, etc., the values are always going to be positive. So this really doesn't have any bearing on the absolute values. I can rewrite this as the limit as n approaches infinity of the nth root of n for n over 3 divided by 7 to the n, right? And now I can go ahead and employ the nth root, and that's going to get rid of this, the n that's affixed to the 4 as an exponent, and the 7th, the n that's affixed to the power of, or the nth root, the nth power of 7, all right? But we can't do anything with this guy yet, this n to the, with this guy right here. So here's what we're going to do algebraically. We're going to rewrite this as the limit as n approaches infinity of n to the 1 over n, 4 to the 1/3 divided by 7. All right. Now, this is just a real number. All right. So that's like the third root of 4 divided by 7. And so realistically, all we have to do is just find out what happens to n to the 1 over n as n approaches infinity. All right. So let's just kind of hold off on this. I'm going to put a star next to it. And let's just find our limit as n approaches infinity of n to the 1 over n. And because we have an n in the in the exponent, this is a classic candidate for our logarithm, all right, to be able to implement a logarithm. So remember, we have this trick. Let's let y be equal to n to the 1 over n. All right, so we've seen this technique a number of times. We're going to take the limit as n approaches infinity of y is going to be equal to the limit as n approaches infinity of n to the 1 over n, okay, which is precisely what we're trying to find, is this guy here. And then we're going to introduce a logarithm. So we're going to have the limit as n approaches infinity of ln y is going to be equal to the limit as n approaches infinity of ln n to the 1 over n, right? And then I'm going to move this 1 over n in front, okay, just because that's what we like to use for our logarithm. Just holding this, this is just going to drop down the whole time. So now we're going to get the limit as n approaches infinity of 1 over n times ln of n, okay? Or another way to write this would be equal to the limit as n approaches infinity of ln n over n. And if we go ahead and just use direct substitution, or as n goes to infinity, we'll end up with infinity over infinity. And that is an indeterminate form, which means that we can use L'Hopital's rule. Okay, so by L'Hopital's rule, we just take the derivative of the numerator and the derivative of the denominator. So this is going to be 1 over n divided by 1, right? And we know that if we substitute infinity back in for n, we get 1 over infinity. So this is going to be 0 over 1, which is going to be 0. Now be careful, because again, that is not the limit of what we were originally trying to find. Remember, that's the ln of y. Okay, so recall that the limit as n approaches infinity of ln y is going to be equal to 0. Okay, and again, we're just copying down everything that we have. So we're just going to raise both sides to the e power. And if we do so, we're going to get the limit as n approaches infinity of e to the ln y equals e to the 0, which implies that the limit as n approaches infinity of y is going to be equal to 1. Now, that is not necessarily saying that the root test is inconclusive, because remember, we still had this 4 to the 1/3 over 7. Can't forget about that. So in reality, this whole thing just becomes 1 times 4 to the 1/3 over 7. So that's our limit L that we went all the way back here to try to evaluate. Okay, so remember a few moments ago, we were just trying to evaluate all this, and this was just the algebra to be able to go through and the calculus. And we know that this number, 4 to the 1/3 over 7, we don't know precisely what it is off the top of our head approximately, but we know that it's less than 1. Okay, and so that means by the root test, we know that the series n equals 1 to infinity of, if we go all the way back up, the original problem was n third root of 4 to the n over 7 to the n. So this is going to be n third root of 4 to the n divided by 7 to the n converges. All right, so that's the root test. Okay, the root test is actually one of the easier tests to be able to implement. Okay, and so that actually concludes all of the possible tests that we're going to be looking at for infinite series. All right, so now the next big section that we're going to be looking at is, what do we use all these tests and what do we use infinite series for any sort of reason? Okay, so a suggestion might be to go back, make sure that you have a sheet of paper that lists out all the possible series, all right? So that way you can have those as we move into the next section to be able to study where we try to utilize these power series.